Hello, F sharp. We have come to the end. This is the last video I plan on doing on the topological sort series. And this is going to show you the fastest I have been able to make this thing go. And what we're going to show today is a technique that I got from Fedor Pikus. He's a C++ developer. He has some fantastic talks talking about the idea of branchless programming. And the idea is that with branchless programming, what we do is that we eliminate possible branching points in our code. For example, like if-then statements, that could be a possible branching that could occur. When we left off, we actually got our performance down to 346 microseconds to sort 1,000 graphs. And if you remember at the very beginning of all this, we wanted to get that down to under 500 microseconds. So we've actually achieved our goal. We can stop now and move on. But for fun, I wanted to see if I could make it go even faster. So that's what today is going to be about. We're going to look at making this go even faster using branchless programming. There's actually another video by Creel, is the name of the YouTube channel. And again, I will reference his material as well. And he has a lot of great videos about assembly programming, and some other low-level stuff. And he's got a nice video where he shows examples of doing branchless programming as well. And so between him and Fedor Pikus, those are some of the best examples I've seen of people doing branchless programming. Now, like I said, we want to, branchless programming is about creating code that doesn't have branches in it. And why would we care about that? Well, if we look at this, our last best effort here was this version 11. And what we're seeing is that for that 1,000 sorts, we have 34,000 branch mispredictions. And a branch misprediction is very expensive, because what happens is that the way a CPU works is it has to line up a lot of work for it to do. And what happens if it reaches a branch condition and it guesses the wrong branch, all the work that it had queued up to do, it needs to flush that and restart the pipeline. And my next series is actually going to be fast F-sharp fundamentals, where I'm going to be kind of going from the ground up, from low level, like how does the CPU work, memory architecture, and then build up so you can see like what the implications are for us as we try to write fast F-sharp code. But in this case, as we're doing this profiling, we're seeing, hey, we still have a bunch of branch mispredictions occurring. And one of the trends that you're seeing is as we've improved the performance of this, cache misses have gone down and branch mispredictions have gone down. So I didn't use .trace in this case to find this opportunity. This is me just using the benchmarks I'm getting and as a result saying like, hey, these are my opportunities to improve the performance of my code. So if we go and look at what we had for version 11, what we want to observe is where are branches occurring? Where is it possible for us to have branches? And there's a few different places where it could be occurring. Well, first of all, we're calling into the runtime here. So the gc.allocate uninitialized array, I'm calling the .NET runtime. There may or may not be branches in there. I'm not sure, but it's code that I didn't write. So there's a possibility of branches occurring there. There's also this possibility of this stack alloc. This could possibly have some branching logic in it, because I mean, it has to check to see if like, hey, am I overrunning the stack? Am I allocating too much? So there's a possibility of branches in there. Other places where branches could occur. You have while loops, checking this condition. You have another while loop. So like each time it goes through like, hey, is this condition met yet? Is this condition met yet? If it is, continue with this code. If not, you need to skip it. Now, CPUs are exceedingly good at correctly predicting loops because they are so fundamental. So Sometimes what you can do is you can unroll a loop. So instead of it being a loop, you're just manually writing out all the code. And that is one way that people do some branchless programming. That's not what we're going to do. And the reason I caution against it is a lot of the time compilers will do it for you, or the CPU will do it for you automatically. And so it's not something that you're likely getting the benefit of this idea of loop unrolling already. So it's not something I would reach for immediately. Again, what you should do is benchmarking. You can try it. I'm just telling you, it's not the thing that I reach for immediately, because a lot of the time it's already happening. Now, other situations which can cause branching in your code, like I said, is these if-then statements. So here's one here, like, hey, if source counts is equal to 0, then we want to take some action. And another example here is like, hey, if source counts equal to 0, then we want to take some action. Okay, so this is where branching can absolutely occur. And we know for our algorithm, what this is doing is saying, hey, are there any more incoming edges for this node? And if not, then this node needs to be added to the ordering of our topological sort. So that isn't always the case, though, because as we're running the algorithm, like, hey, we'll remove the first edge. Oh, there's still some incoming. Okay, we don't want to do it yet. Okay, we remove another edge. Okay, now it's actually 0. Now we could add it to our topological sort. So this very naturally is a place where branching is going to occur. And it's likely that the branch predictor will miss this sometimes, not every time, but sometimes, just because it will appear slightly random to it. And the CPU is extremely good at picking up patterns, as you will see later in the video. But by the very nature of this thing, it is random whether this is actually true or not. So these two if statements, this if statement here, and then this if statement here, are great candidates for applying the idea of branchless programming. And so if I take on version 12 is where I go branchless. Now, Zen mode, sweet. We got them both side by side. So what is different between these two? Let me try to get them lined up here, sort of the exact same spot. So it's not quite lined up, but pretty darn close. So left version is the fastest we've gotten to date. Version on the right is where we're going to go branchless. And the difference is here, is these lines of code here. So on the left, we have this if-then statement, and on the right, we do not. We have something else. So what I'm doing here is a classic technique for branchless programming, and it's the idea of using a Boolean as an int. And what I'm doing in this case is that over here, I'm saying if this is true, then I'm needing to increment something over here. That's what's going on in this code. It's like, hey, if this is true, if this count is equal to 0 now, I want you to insert this node ID, and then I want you to increment the number of results that I have. Over here, what I do is I'm doing that same check. Is I'm saying, hey, source counts, is that equal to 0 or not? And I want to use it to increment this result count. Now, the problem is this is going to return a bool. And in F#, it does not have implicit conversion from a bool to an int. You can do that in C. You can do that conversion in C#, but in F#, it does not let you just implicitly cast this to what you want, which is why we need this retype function. And so retype, what is retype? Let's go look at it. So retype is stupid unsafe, is why, so be aware. And what retype is we're taking advantage of a feature of F#, which is that you can inline IL. And for those of you who do not know, IL stands for intermediate language. It is the language that C#, F#, and VB turn into when they get compiled. And then the runtime takes that IL and then turns that into machine code for you. And so IL is this intermediate language that all these other languages compile to, and that intermediate language then gets turned into whatever the machine language that your computer architecture needs it to do. So retype is some IL, and what it does is it says, hey, this, like whatever the type you think this is, it's now this. And what we're doing is we're saying, hey, that bool, yeah, let's just interpret that as an int now. And now we're going to go ahead and use it. Now, the reason you can do this safely is because in .NET, bools are bytes underneath, and the bool representation of true in terms of the bytes is equivalent to the integer representation of 1. So a bool is going to be a byte, which is going to be 0000001. 01, okay, whatever. That last that last bit is going to be a 1. And the same is true for an int. And so you can do this conversion, and it's actually going to give you a 1 underneath the hood. So what we're doing is we're saying, hey, evaluate this Boolean expression, interpret it as an integer now, and then I'm going to use that to increment. And what this means is that this code is going to, all of this code is going to run every single time, but it's only actually going to increment when this is evaluating to true. If it's evaluating to false, then this increment is 0. And so you're not actually performing the incrementation here. So like over here, you have to check, is this true or not? And if it's true, perform the incrementation. Over here, you're evaluating whether it's true or not. If it's false, it's a 0. And so when you add 0 to the result count, it's not actually performing any incrementation. Only when this evaluates to true is it 1, and then it's actually doing the incrementing of result count. Same thing is done down here. It's the exact same code for this kind of conditional incrementing of a value. And this is this code here, this again, check, hey, if source count is equal to 0, then we want to do some work here. In this case, no, I kind of got this like reordered. Let me put it in the same order so it all looks the same. So again, we check, is it equal to 0? If it is, increment is going to be equal to 1, and so it will actually increment the result. If this is not equal to 0, it will evaluate to a 0 integer, and therefore when you add 0 to result count, you don't actually end up incrementing this value. All this is doing is removing all the branches, is removing the branches from the code. So there's no longer an if statement. So what it means is that we're not going to run the risk of saying, hey, the branch predictor predicted the wrong branch, therefore all the work it had lined up, it needs to flush that out and reload the pipeline to do some work. So does that yield any performance benefits? Well, that's a great question. So let me here exit Zen mode, and we're going to come back here. Well, we went from 348 microseconds to 249 microseconds. So about a 40% improvement in speed. And like we said, we are doing this branchless programming. We wanted to reduce the number of branch mispredictions by just getting rid of the branches. And we can see this goes from 34,000 branch mispredictions down to 14,000 branch mispredictions. So the CPU, the branch predictor, doesn't have to do as much work because there are just fewer branches and you can't mispredict a branch that isn't there. So yeah, this can have really significant performance improvements like this. And this is massive, especially considering at this point, like how much we've already improved this algorithm, the fact that there's still this much low hanging fruit, as I would put it, to dramatically increase the performance. Like that's really exciting for me. So that's super fun. I'm not actually using this in our engine code yet because we don't need it. Like I know it's there and it was fun and it's exciting and I wanted to share it with you. But like I said, we've already passed our threshold for performance. I just thought this was fun and an interesting challenge. Now, there's a caveat here. So this is really great. But as I was playing around, I found some interesting behavior. Remember how our benchmark is doing a topological sort on 1,000 random graphs of the size that I'm interested in? Well, in my playing around, I also ran the benchmarks, but with only 10 graphs instead of 1,000. And when I did that, I see some very interesting behavior. So look here, version 11 was our previous best. And when it's only 10 graphs that it's sorting in this benchmark, it does it in 1.49 microseconds. The branchless version, which we just showed was much faster for 1,000 graphs, is actually much slower when it's only 10 graphs. What is going on? This is bizarre. Well, the answer is right in front of us. Look at, so first thing is like, okay, number of branches between them. The branchless version has fewer branches than the underlying code. Okay, that makes sense. Similar number of cache misses. Branch mispredictions are the same. So our branchless version has the same number of mispredictions as the branching version of our code. Now let's go back and look at our previous. So this is for 1,000 graphs is what we're looking at right now. And version 11 for 1,000 graphs had 34,000 branch mispredictions. In our branchless version, version 12, for 1,000 graphs, only had 14,000 mispredictions. So far fewer mispredictions, much better performance on 1,000 graphs. When we go to 10 graphs, the performance of our branchy version is better than our branchless version. What is going on? Now, something to note. Let's come back to the code. It's always about the code, man. In our branching version, version 11, it checks this condition, and if this condition is true, it will do some additional work. But if this condition is not true, it can skip this work. Same thing down here. If this branch is false, it can skip this work. In the branchless version, it always has to do the work every time. Even if it evaluates to 0 and therefore like doesn't do the incrementing, it's still like having to like evaluate it and then add 0 to the result count. So the total amount of work the CPU has to do is actually larger in the branchless version. We've just removed branching, so it's better at predicting at what work it needs to do. So branchless almost always is trading computation for speed because, well, it's doing a little bit more work, but the fact that it's doing a little bit more work and not branching often yields incredible benefits because mispredicted branches are so expensive. So if the CPU is able to always correctly predict which branch to take, the branchy version, this version here on the left, will be faster because it is fundamentally less work. If the CPU cannot correctly predict the branching, this version, which has a little bit more work, will be faster because it doesn't have to pay penalty for mispredicted branches. Now, what is going on here in this scenario where we only have 10 graphs? It's a great question. I don't fundamentally know the answer yet. I am still working on it. I have a theory, though. When you only have 10 graphs, the CPU branch predictor, well, see, and this is where things get really difficult. AMD and Intel do not want to explain their secret sauce exactly of how their branch predictors work. They want you to like know how to work with the branch predictors so that you can create high performing code, but they don't want to like really explain to you how exactly it's working, which makes sense. I mean, it's proprietary secret. It's why you would buy an Intel over an AMD or buy an AMD over an Intel. But branch predictors have memory, and they can observe patterns in your data. And if you're coming and processing over the same chunk of data again, and its memory is long enough, it can say, hey, I've seen this data before. I've seen this layout before. I know what to do in this situation. So when your sample size for your benchmark is small enough, if you're only using 10 graphs, in my case, I'm using a Zen 2, and you can see that here. I have an AMD Ryzen 3900X. So like, you know, back in the day, this was a scorching CPU. Now that the Zen 4s are coming out, I'm like, do I need to upgrade? I don't need to, but I want to, whatever. But like, this thing has a fantastic branch predictor, tons of cache. So it has a long memory. So when it's only 10 graphs, it's able to remember like, oh yeah, I've seen this graph before. I know what branches to take. But once the sample size gets large enough, it can't remember all the different graphs that it's seen. So it can't remember what the correct predictions were. So now the branchless version is far superior to the branching version. So what's the takeaway for us? Wow. Like the data you use for benchmarking is critical. Now, if I was writing this algorithm where like, yeah, I only have a very few number of graphs that I need to do topological sorting on, I would want to put that truth into the data I was benchmarking. Having statistically representative data for benchmarking is critical for you to get the correct outcome. If I only had a few graphs, it would make sense for me to only benchmark 10 random graphs. And like, yeah, that would be like the realistic performance if I knew I had to do that over and over and over and over again. On the other hand, that is not my situation. I have random graphs, and it will potentially never see the same graph ever throughout the course of the simulation. And so I want to have enough random graphs in my benchmark that branch predictor can't memorize my data and therefore like always predict the correct branch. So this version is more representative of my use case. And I've actually taken this up to like even more graphs and even more iterations. And this is this percent difference in performance is consistent. It's only once it like drops down to like 100 graphs in that range that the branch predictor is able to perfectly predict branches, which is actually remarkable that it has that much memory. Very impressive. So Yeah, I'm still digging into it. That's kind of what my theory is, but I don't know that for sure. If you have any insight or resources I could look at, I would love to hear about it. This has been just an absurd amount of fun for me. I hope that you have found it useful. If you have questions or ideas or comments, I would love to hear them. Please email me, hit me up on F# Slack, leave a comment, whatever. I don't care if you subscribe. I hope you're enjoying it. And if there's something you want me to cover, please let me know. My next series is going to be on fast F# fundamentals, where we're basically going to go from the bottom up. Like, let's look at a CPU's architecture and its memory architecture, and then kind of use that knowledge and kind of build up an understanding of how to write fast code. And then the next thing I'll do is I'll take another algorithm or something and then like apply these techniques to make it faster and faster and faster. So I hope you're finding this useful. I really appreciate you spending some time with me. Until next time, have fun writing that awesome code. Bye-bye.